In this video, we are going to see Nyquist stability criterion problem solving, and we have discussed the theory of Nyquist stability criterion in the previous videos. Okay, we consider and explain here to explain in brief what is Nyquist stability criterion. Okay, in Nyquist stability criterion, we take a Nyquist contour in which we take the radius of this semicircle to be r, and we assume r is tending to infinity, and we take the directions in clockwise direction so that the enclosed area is in between these lines from the principle of Cauchy's principle of argument. Okay, now this is called Nyquist contour. Okay, now as r tends to infinity, we take this as plus infinity and this minus infinity and this point 0. Now we can divide this into three sections. Okay, let's write this as section 1, and this whole semicircle, the arc, take it as section 2, and this part minus infinity to 0, take it as section 3. Now from Nyquist stability criterion, we have seen if we are given a function g of s times h of s, and if we substitute each and every value on this Nyquist contour into this g of s h of s, we're going to get a set of values. If we plot these set of values in a different complex plane, okay, in a different complex plane, then we're going to have a closed figure. Why we have closed figure is, suppose if we start at 0 here and go over this 0 to infinity and go over this arc plus infinity to minus infinity and come back to 0, we're going to have the same value when we substitute 0 in g of s h of s. So if we start at a point and however it goes, it is going to come back and meet at the same point. So it is going to be a closed plot for this g of s h of s. Now from Nyquist stability criterion, we know that if we are given g of s h of s and if we plot the values of g of s h of s for corresponding Nyquist contour, then the encirclements around -1, if we take them as n and I take the reference direction to be clockwise direction, then n equals z minus p. Now p indicates number of poles in the right half of S-plane, and this number of poles are corresponding to g of s h of s. Okay, g of s h of s. And now z equals number of zeros of 1 plus g of s h of s, and zeros of 1 plus g of s h of s are nothing but poles of closed loop transfer function. Okay, now we know n z p. Okay, but from the given equation g of s h of s, we can find out p directly, and when you plot for this corresponding Nyquist contour and do this and see encirclements around -1, then we'll come to know what is n. Based on that, we can calculate z here. Okay, this z is nothing but zeros of 1 plus g of s h of s. If they come out to be finite value, okay, then we are going to have poles of the closed loop transfer function, where closed loop transfer function is g of s over 1 plus g of s times h of s. Okay, we'll have 1 plus g of s h of s in the denominator. Now zeros of this are nothing but poles of g of s by 1 plus g of s h of s, which is closed loop transfer function. In this case, this system will be unstable if z comes out to be finite value. Okay, if it is non-zero. Fine. This is Nyquist stability criterion, and for all this analysis, we assume g of s h of s is analytic over the Nyquist contour. Okay, and we'll come to see a situation where it won't be analytic, and we solve those problems in a different way. Okay, let's see how we are going to calculate g of s h of s values for all these sections 1, 2 and 3. Okay, to analyze this better on the Nyquist contour, let's take an example where g of s h of s equals 1 over 1 plus st1 times 1 plus st2. Now, if we take this one, now we know how this plot looks when omega is changed from 0 to infinity. Okay, we have seen this in polar plots of this function. Now we know why the polar plots are taken from 0 to infinity as omega is tending to these values, because we were actually looking how this plot for this g of s h of s looks for this corresponding section number 1 in Nyquist contour. Okay, if you know the Nyquist contour plot for that particular section, we can construct for the whole Nyquist contour, and we'll see in a minute. Okay, now when omega is changing from 0 to infinity, if you look at the magnitude of this plot, okay, g of s h of s function, the magnitude function m is going to be 1 over square root of 1 plus omega square t1 square times square root of 1 plus omega square t2 square, right? And phi is going to be minus tan inverse of omega t1 minus tan inverse of omega t2. Fine. Now, if you take omega 0 to infinity, magnitude and phase values for them correspondingly, this will be 1 and 0. Fine. And phi is going to be 0, and it goes to minus 180 degrees. If you plot this particular plot, okay, for that corresponding values, we are going to have a plot like this. Okay, and the directions are in this way. As omega, this is the corresponding value for omega equals 0. Okay, and this is for omega equals plus infinity value. Okay, now if we substitute, now this is for the section 1. Now let's see how this plot looks for section number 3 when omega is varying from minus infinity to 0. Now if you take at magnitude value, if you substitute omega minus values, anyway you're having omega square here, so negative sign is not going to impact the magnitude. Magnitude is going to be exactly the same, okay, however it was for the section 1. Now the only thing is phi. What will happen to phi? If you substitute omega negative values, then what happens is tan inverse of, let me write down here, tan inverse of minus x is minus tan inverse of x. In that case, what is going to happen is phi will become, okay, for this third section, let me write down it here, tan inverse of omega t1 plus tan inverse of omega t2. This is how the function is going to be. Okay, in this case, when omega is minus infinity, we're going to have a value of plus 180 degrees, and it decreases, and somewhere it goes to 90 degrees and decreases. When omega is 0, you'll have 0 degrees. It means the magnitude is not going to change. Okay, it is going to be exactly same as the first section for this third section, but the phase angle is exactly reverse. So it means we're going to have a mirror image of this plot. So the mirror image is going to be something like this. And the way it is going to be is, as we are changing it from minus infinity to 0 in this direction, so we will have plot points like this. Okay, minus infinity to 0, right? So this is how the plot looks when we take care of this first section and third section. Now this looks almost like a closed one, right? Closed figure. Now what happened to the second section of the Nyquist contour? Where did it map from? Okay, if we look at it carefully, when r tends to infinity, okay, the whole plot is going to be around this point, okay, which will be nearly in the 0 section. Let's zoom into this area and find out how this plot is going to be converted when we substitute those values of this semicircle into g of s h of s. Okay, let's look for this second section and that second section is going to transform like this. Okay, for that let's take s as r times e power j theta. Okay, and theta is this value. Okay, theta is this value. Now let's take s equals r e power j theta. Now if you substitute this value s equals this in g of s h of s, we can rewrite that equation as 1 over 1 plus r times e power j theta times t1, okay, times 1 plus r times e power j theta times t2. Fine. Now we know that r is tending to infinity. It's a very high value, so we can neglect this one. We can rewrite this again as 1 over r times e power j theta. We have t1, t2, and r times e power j theta again. We can rewrite this as, okay, 1 over r1, r2, t1, t2 times e power minus j 2 theta. Okay. Now we can write the magnitude of this equation, which is r1, r2, t1, t2. This is the magnitude, and the phase angle we can write as minus 2 theta. Okay. Now if you take values of theta, they're going to change from we are going from plus infinity to minus infinity. Okay, at plus infinity the angle theta will be plus 90 as we are measuring it at in anti-clockwise direction towards 0 and then minus 90 degrees. Now what will happen to phi? Phi is going to be minus 180 degrees. Okay, and when it is 0 it goes to 0, and in between suppose if you have plus 45, it will be minus 90 degrees. Okay, similarly when it is minus 90 it will be plus 180 degrees. Okay, these are the values, and as r tends to infinity the magnitude tends to 0. Okay, suppose assume that r is a high value not tending to infinity, then we are going to have the magnitude of this m to be some finite value which is closer to 0. In that case, if you plot only that particular function, how it varies is it will be at minus 180 degrees, and the plot looks like this. Okay, it goes like this and meets here. Okay, in this direction. As r tends to infinity, m will tend to 0, so this whole circle reduces to 0 and will be corresponding to one particular value that will be just one value at the center. That's the reason why you don't see that particular second section in this plot. Okay, so it is going to tend to 0. That's why we don't see it. Now let us draw some conclusions. Let me run this all calculations here. Now we know that section 1 and section 3 are corresponding plots for g of s, h of s, or for say matter for any function are going to be exact image reflections of the plots, and section 2 is going to map to a point on the origin, so you won't see that particular plot in the corresponding plots for this Nyquist contour. So now we know how to plot for all these corresponding values. Now we are having this transfer function and this is a plot for it, right? So now Nyquist stability criterion says if you are given g of s, h of s, okay, we know now g of s, h of s corresponding function, which is this. Okay, now we know the plot of g of s, h of s on a complex plane, which we have it here. Okay, which we have it here. Now we want to see whether g of s over 1 plus g of s h of s function, or if this g of s h of s is connected in a feedback loop, okay, then will the system be stable? That we will find out from this Nyquist stability criterion. Now let's see, if I take this is minus 1, we know that these plots are going to touch at 0, okay, origin. Now the number of encirclements around the origin, okay, in clockwise direction, we know it is 0. Okay, and n is z minus p. Now tell me, the values we know will be p from this g of s h of s. Now assume t1 and t2 are positive values. Then the poles of this g of s h of s are minus 1 by t1 and minus 1 by t2. And now tell me, these two values are going to be in the left half of this S-plane. So these two poles are not covered by this Nyquist contour. As a result, we can say the number of poles is 0. Remind you again, this P is number of poles covered by this Nyquist contour. As these two are not in the right half of S-plane, they are not covered by this Nyquist contour, so P is 0. Now 0 equals z minus 0. Now z should be 0. Z is what? The number of zeros of 1 plus g of s times h of s. If the number of zeros of this are 0 in the right half of S plane, then number of poles of this g of s h of s by 1 plus g of s h of s will be 0. I meant the poles of this closed loop transfer function will be 0, which means the system is stable. So based on this, we can solve other problems. We'll see in the further coming videos some real problems with real values. Okay.